let's get started. Good morning, everyone. My name is Standa Živný. I'm the chair of the LMS Computer Science Committee, which does a few things, and one of them is to run this colloquium every year, usually in December. So usually we try to find a topic which is at the intersection of mathematics and computer science. And this year we have a combinatorics and computing, which, if you ask me, is perhaps the most interesting and the most influential topic in this space. So we have 4 great speakers today. Hopefully you can hold up the copy of the schedule. There are some there's breaks, and there's a lunch provided in the room where there's coffee and croissants now. So let's just get started. Our first speaker is, I'm going to butcher the name, but Böttcher from LSE, which yes, all right. Talking on random process and quasirandomness for decomposition problems. So, Julia, please.
I have to find out where to stand so that I don't stand in front of them.
Anywhere there is perfect.
Yeah, but they want to see. Or I don't know. Okay, thank you very much. I'm very happy with the invitation to talk here, and I think this event is a great idea to bring maths and computer science together. I think it's excellent. My only problem when I'm preparing the talk was that I thought, I don't really do things anymore too close to computer science. But anyway, I still want to tell you something of the area where I usually do research, and so this is more on the purely combinatorial side, and maybe introduce some problems to you and some techniques that we use in order to study this problem. Now, I saw that in the audience there are so many combinatorialists, so maybe for them I aimed it a bit too low level, but I want to include everybody. So I hope I managed to just tell you some stories, and I hope that everybody can take something from it. So my topic is really I want to talk about decomposition problems and how we use random processes and also quasi-randomness in order to address these kind of problems. And of course, I should kind of carefully introduce all these things and also say what I mean with this and give you some examples. So that's what I will do in the first part of the talk, which is maybe the more technical part of the talk, where I also try to give you a feeling of what kind of methods do people use, and I will have some rather broken down, easy calculations where I show you what are the kind of arguments we use, but we won't do anything complicated today. And then in the second part of the talk, I want to mention an array of related problems that fall into this framework, but I want to show you how they fall into this framework. And it's really just a selection. There are many, many more. All right, so let's get started. So I should first define what are decompositions. And for this, let me first define what is a packing. So I will talk in the talk, I will talk about graphs and also hypergraphs, but let me start with graphs. And for a graph, I can take a collection of graphs, which is G1 up to GK over there. And I might want to pack them into some separate graph, graph H. And packing them into here means I find copies, not necessarily induced, of these graphs, which are edge disjointed. They don't have to be vertex disjointed, but they're edge disjointed. Another way of saying this is I color some edges in this graph over here so that this is exactly a copy of the corresponding graph over there. And I don't need to use all the edges over here. These copies here, they're not induced, they're edge disjoint, but they might not be vertex disjoint. Okay, so that's the packing. And if this packing uses up all the edges over here, I don't have any black edges left, then this is what we call a decomposition of the graph H into these other graphs. And sometimes it's also called a perfect packing. And I just say that because there's also something we call almost perfect, which is when we use up almost all the edges here, which is a bit of a vague term, but I want to leave it vague, and I might want to say that later. That's why I'm saying that here. All right. So that's the kind of object I'm interested in. I'm interested in when do these packings of some graphs into another graph exist. Now, in general, deciding whether some graphs can be packed into a graph, that's a really hard problem. That you can easily see by even so, if you take a graph, you take its complement, and then ask this complement, does it pack together with the Hamilton cycle, so a cycle through all the vertices in the complete graph? Well, that just means finding a Hamilton cycle in the original graph, right? And that's a hard problem. So packing is certainly a very hard problem. Therefore, what we are interested in combinatorics often is kind of to find some situations where we can pack, right? So to just find some statements, if this and that is satisfied, well, then we can pack these graphs. So some easily verifiable conditions. And as I already tried to indicate, you can do the same thing analogously for hypergraphs. So in this talk, for me, hypergraphs will always be uniform. That means all the edges, each edge has the same number of vertices. I will have R uniform hypergraph, meaning every edge has R vertices, and then you can make the same definition, exactly the same. Okay, good. So these are decompositions. Now let me go to some object that is strongly related and of interest also in some other communities. This really comes from more from the statistics side. So designs. Okay, this is a bit of a mouthful, this definition, because I have many parameters, n, v, r, and lambda. So what is a design? Well, I have my ground set, which is just for simplicity, the number is 1 to n. And then I want to take subsets of this ground set, and I'm taking a set of subsets, and that's somewhat important. I don't have a multi-set, but I have a set of subsets. So they have distinct subsets, and I call these subsets blocks. That's just because there are too many sets floating around. So I have these subsets I call blocks. So I have blocks. So I want to select blocks with the following property. Each block should have the same size. That's one of my parameters over there. Okay, that's easy. But now the second property is more complicated. So now whenever I take a subset of my ground set of size R, and you should think of R as being smaller than B. So I take some subset of size R, then this subset is contained in exactly lambda blocks of my block design. Yeah, so this is a design that somehow comes from the theory of how should we design some experiments where, I don't know, maybe you have a set of people and they have different characteristics. One thing that you can then do is kind of block people with similar characteristics into one group, because, I don't know, you do some, I don't know, test some medicines or something like this, then you would want to compare between two people with the same characteristics if you test different medicines. So you put them into blocks by their characteristics, and then you somehow, but you somehow want to still do your experiments to cover these blocks evenly. So that's more or less the idea where this comes from. But so for me, this is really just a mathematical object of interest. When can I define such a block as such a block design for what parameters? Right? That's the question. And now again in this talk, for simplicity, let me get rid of one of the parameters. So this lambda, that's blue here or green. Let's get rid of it. Okay. So it's exactly the same definition, only that now each set of size R is contained in exactly one block. Yes. Right, so I mean, actually, you all know things of this type. One example is a funnel plane. This is a 7-3-2 design. What does it mean? I have 7, and my ground set is of size 7, so these are my 7 vertices here. My blocks are of size 3, which I just kind of indicate here by these colors. Yeah. And it has the property that every pair of vertices is covered is contained in exactly one block. Okay, this can be also, how does it connect to what I just did before? Well, this can also be seen as the decomposition of the complete graph in 7 vertices into triangles. So I have all the edges on my 7 vertices, and each of these colored things here, I consider them as a triangle. So it's this edge, and this edge. Right? And since every pair is covered exactly once, then that will give me a decomposition of the complete graph into triangles. Okay. So more generally, whenever this last parameter R is a 2, then I get a decomposition of the complete graph into copies on n vertices into copies of the complete graph of B vertices. And when R is now bigger than 2, then we have the same thing in hypergraphs. So these are really just decompositions of complete graphs or complete hypergraphs into complete graphs or hypergraphs. And the question is still, when do they exist? So that's really something that design theorists would like to know. For which parameters can I find such a design? And then I might, once I know this, I might ask some complicated questions like, what kind of properties can I ask of a design, or how many do there exist, or something like this. Okay, and there's lots of applications. I already said experiment design, but there's also applications in error correcting codes, cryptography, lots of things that are connected to computer science. But I don't want to claim that I'm much knowledgeable about these applications. That's why let me just mention it, but go on with the combinatorics. Right. So then, I mean, now that we know this is kind of just the question of decomposing either complete graphs or complete hypergraphs into smaller complete graphs or hypergraphs, we want to know when do they have a chance of existing? And there are some very natural obstructions for them not existing. And let me just illustrate this with the example of that I have them in the graph case, and I just want to decompose a complete graph on n vertices into triangles. Now, one very easy condition that we need is that the number of edges in my graph, which is n choose 2, should be divisible by 3 because I want to decompose it into these triangles. Okay. The second condition is also easy, but one needs to think maybe for 2 seconds more before seeing it. I am claiming that n-1 has to be divisible by 2. Well, that's if we look locally at the vertex, right? If I have a triangle on this vertex, then it will take away exactly 2 edges. And I need to cover all these edges going out of the vertex. So the number of edges coming out, which is n-1, has to be divisible by 2. Right. And so these things we call divisibility conditions. And then if you think about it, then this just means that n has to be congruent to, I think, 1 or 3 modulo 6. But I might, I should have thought about this before. I might mix up these two numbers. Anyway, 2 particular congruent classes modulo 6. You can work it out. And otherwise, if that's not the case, then of course it can't exist. But then the next question is, of course, what if these divisibility conditions are satisfied? Does the Kn then have a decomposition to triangle? And you can play the same game for other parameters, so for hypergraphs as well. By saying, well, again, looking at the number of edges should be divisible by the number of edges of the object that we want to decompose into, but then also looking at vertices, or maybe if you have a higher uniformity hypergraph, pairs of vertices, and so on. And these all give you some divisibility conditions, and they're really exactly like this. Yeah? So these are necessary conditions for the designs to exist. And then there was a very famous, for a long time open question, if whenever these conditions are satisfied, then we get a design. And this is actually not true. There are some counterexamples to that, but only small counterexamples were known. I mean, once you fix your parameters, B and R, then only for certain small n, some counterexamples were known. And that's why the conjecture was that apart from these small counterexamples, we should always be able to get a design if the conditions are satisfied. And that was proven in a big breakthrough, first announced by Kiewasz, but then not long afterwards, also Glock and Ostrus came up with the proof that is indeed the case, at least if n is large. So the caveat here should be that, and that's the case for most results in this area, is that the tools that we currently have for approaching things like this, which I want to tell you about a little bit, they always require that the number of vertices I want to work with is really large. And that's why it's always, you should think of R and B being fixed, and then I take n very large. And in practical applications, that's too large. So, I mean, it's not so nice if you have these actual applications in mind. But it's a start, and it was a very big breakthrough when this was finally proved.
So how large is large?
Oh, I actually don't know. I mean, it's maybe, but it's not, it's not, I mean, if you know regularity lemma kind of constant, it's not that. We use random processes here, and from this, I don't know if anybody actually explicitly calculated. But probably something like 10 to the 10, let's say, something like this. Yeah. So for me, that's a rather small constant, but for the computer scientist in the room, it's probably a rather large constant. All right, good. So what I want to do next is I want to tell you a little bit, if I want to prove something like this, what kind of ingredients go in there, and then I should tell a bit about also kind of the history of what was done here, at least part of it. Oh, and I should also mention, for the graph case, this was actually known already before. So it's really the hypergraph case that was open. For the graph case, this was done using methods from algebra, and which is also some very nice tools. But unfortunately, it seemed completely impossible to use these methods and then get something for hypergraphs. And I mean, just using algebraic ideas, of course, kind of means we want to exploit the symmetry. I mean, of course, if we are packing things into a complete graph, then everything I'm doing is very symmetrical, and then I have some hope of exploiting that. And then the solution to this was really different in the sense that kind of we didn't know how to push these methods further. And then one thing in the last 50, 60 years, maybe that people did whenever they didn't know how to use other methods, they said, okay, then let me just do something randomly. And this is surprisingly powerful. And I want to show you here how this works. And doing something randomly, of course, means you kind of lose a lot of symmetry.
Show you this question.
Yes, please, sorry.
In the graph case, do we also need that n is very large, or can
You need the n is large, but probably not as large. I don't know actually how large n has to be. That I don't know.
And the two proofs, are they very different?
They are different, and I would say, let us say what is different, but not for kind of the first part that I now tell you, because that actually relies on some older work. They're then different in one step that I will come back in the end. Right. But let me also say that, yes.
Sorry, just for the benefit of people watching online, if you have any questions from the audience, could you just repeat it?
Oh, yes, I'm sorry, I completely
Okay.
forgot.
So-
I will try to do that from.
Thank you.
Right, so the last question was if the proofs are very different, and some part is in common and some part then is different. And I will say a little bit about this. And let me just also say, I mean, it's really been very nice and also very influential for the area that there were these two proofs, because they allowed us to prove various other things and so on. So, I mean, often it's actually very good if two different groups arrive at the same goal with different techniques, then that usually fertilizes the whole area in two different ways. Okay, right. So let me now, okay, we do something random. Let me try to explain that a little bit to you. And let me try to go slowly. And for those of you who have seen these kind of methods, in particular the little nibble method before, then now probably you can kind of think a little bit about something else. But anyway, I want to explain this anyway. So let me start with the question: what if I don't want to get a decomposition of the complete graph into triangles? I'm going to stay with this example because it really makes a lot of things easier in the illustration. So I don't want to get a decomposition of the game into triangles, but I want at least to get an almost perfect pack. So I want to pack triangles into my complete graph so that almost all the edges are covered. Yeah, all but 1%. And we want to do something random. So maybe the first attempt is that let me just choose random triangles. What does it mean? It means I have all my possible triangles here, and maybe I say for every triangle, oh, well, with probability P, you're present. And I can choose my P appropriately. And that won't work, but let's do it anyway so that we see what happens. And so if we do that, then of course in expectation we choose P times n choose 3 many triangles. And that means we need P of the order 1 over n. And you can ignore this constant. That's not so important. Maybe I could have put P there or something. But you need P of the order 1 over n so that we have a chance of getting as many triangles there as we want. And now, of course, if I just choose triangles randomly, my worry is, okay, what if two triangles overlap? So let's try to think about these overlaps. So if let's say I already chose one triangle, then in expectation, how many triangles does this thing overlap? How many triangles that I choose does this thing overlap? Well, there are, so how can I overlap with this triangle? Well, I have 3 edges where I can overlap. And for each of these edges, there are n-3 possible other triangles that can overlap in this edge, right? So I have 3 times n-3. And then each of these triangles appears independently with probability p. So that's the expected number of triangles that I'm overlapping with. And if my p is of this size, then this is bigger or equal than 1. So that means, I mean, not every triangle that I choose needs to overlap, but since I'm choosing quite a number, there will, with high probability, will be some overlapping triangles. So we don't get a packing just by choosing triangles randomly. Now, this is also not surprising, right? We wouldn't have expected that. But there's a standard trick that I can do when I kind of do some random process and get some object that is not quite what I want. Which is called the deletion method. I mean, I could say, now I have all these randomly chosen triangles, maybe some of them overlap, but then let me just delete those that overlap. Okay, so let's try to estimate how many triangles I would need to delete. And I'm not doing that directly because it's a bit more complicated. Let me instead just try to estimate the number of pairs of chosen triangles that overlap. So and it's an expectation. So I made my first triangle of my pair there and choose 3 many possible things I can choose. We already said each chosen triangle has that many triangles it can possibly overlap with. And then for 2 of these triangles, there's a probability p squared. So each of them is their probability p. Now let me, if you rearrange this so that we have the expected number of triangles that we choose over here, then I have roughly this factor 3 times Pn in addition. And that means if P is kind of that size, as I said at the start, then somehow this is bigger than the expected number of triangles that I choose. So that's bad. I mean, okay, so the number of overlapping triangles won't be more than the expected number of triangles, but just kind of this funny little calculation that I can do as a good proxy that somehow gets too big, but it means that indeed most triangles will actually overlap in this case. So one can make this precise, but let me not do this here. Okay, so this is bad because it would mean that we delete most of our triangles again. Okay, but I wanted to do this because one thing that one sees here is that if I now choose my p smaller, so if I make this constant here bigger, let's say, I put 1,000 here or something like this, then this here also gets smaller, and this here gives me the fraction of the chosen triangles that overlap, right? So that means if I make p smaller, then I can make this fraction of overlapping things also smaller, and then I'm in a much more happy place again. The problem is just that then I don't have enough triangles yet. So then I should think about, I don't have enough triangles yet, so what do I do then? And that was indeed, and that will be my second attempt, the insight of Rödel, how one can deal with this situation. And that was already done in the 80s. So already in the 80s, he proved not how do I get a design, but how do I get an almost design, so an almost perfect type. And this was also very influential because it was not just important for this area, but in lots of other areas, graph coloring, lots of other things. This really led to new results. Okay, so what's the idea of the Rödel level? So we do exactly what I just said, but we do it with a smaller edge probability. So that we maybe choose 1% of the triangles in my first round. And 1% probably isn't the right number, but just for illustration purposes, let me choose this number. So we choose 1% of the triangles in the first round. And there are some overlaps, but this is a small percentage of the triangles that I choose, as we just saw in our calculation. And then, and then I kind of just ignore those that overlap. So I chose my triangles randomly. A few overlap. I just ignore them and take those that don't overlap, and those I select. Yeah. And then I do the following. Then I delete, so all these edges and triangles that I selected, I now delete from my graph. And I get a graph that is not a complete graph anymore. But yeah, so I have to kind of later think about what can I say about this graph. But I get a graph, and now I want to just continue in this graph and do the same thing again in the second round. So again, select triangles randomly, and ignore those that overlap, and then delete the rest and so on. And what Rödel could prove is that if you do, and I've kind of given an indication what is needed for this in a second, but what he could prove is that you can indeed do these rounds, and you can do them so often that you can cover most of the edges. All right, good. So before I tell you a little bit why this works, why one can do these rounds, think about this for a second. Let me just mention that there is an alternative way of doing this, which nowadays people also use for different problems, and it has also been very influential. But that wasn't done at the time back then, which is what is called the random triangle process. Because if you do this thing in rounds and deleting triangles and round by round, then you could say, well, why am I actually doing it like this? Why don't I start by just selecting one triangle randomly and then taking it out? And then selecting the next triangle randomly and then taking it out and so on. So that's also something you can do. And that's what is called the random triangle process. And that also, of course, I mean, as long as you find a triangle, it of course gives you a packing because you always immediately take out your triangles, so you don't have any overlaps. The difficulty is just that this is harder to analyze. Yeah, so turns out that this, if one does it in the right way, is relatively easy to analyze. Analyzing things like this is really a lot more complicated, and you need to work with things like mapping and inequalities and so on. But this is also something that people nowadays use, and for other problems, it is indeed the right way to go, and very influential. Okay, so that's one remark. Second remark, which I want to come back to in a little bit, is that, so if we do this packing of triangles here randomly, then of course, I mean, at some point, we have to stop. So I said we can cover most of the edges, but we cannot cover all because we take them out randomly, right? And at some point, just randomly taking it out randomly, I will lose control over what the remainder actually looks like, and then I have to stop. So if we actually want to find a design in the end, a decomposition into triangles, then we should have some strategy in mind how to deal with this remainder. And this was exactly the new thing in Böttcher's work and also the work of Bloch, and Osfus. And that's different in the two proofs, how exactly they deal with it. And I want to give you an indication of what one does here, but this is on such a comic level that one won't see the differences of the two proofs. But yeah, this is very hard and gets very complicated. So I really just want to give you an indication. Right. But first I want to say, I mean, why does this work? Going in these rounds, and that's where the next thing from my title comes in, which is quasi-randomness, which is a very important concept also here, and that's what we need here. So we're doing these rounds. Of course, at the beginning, we start with the complete graph, and there everything is nicely symmetric, and we can do these probability calculations as I did. I mean, I only talked about expectations, but anyway, we can rather easily calculate everything there. Now, once you take out triangles, then of course you don't have a complete graph anymore. And then, of course, the calculations look different. I mean, this question, if I have some fixed triangle, how many triangles does it overlap with, and so on, that can, of course, look different. And that complicates the scenario somewhat. And therefore, Rödel's idea was, well, but I mean, maybe I show that whatever is remaining still has some nice properties which makes these calculations somehow go through. Yeah. And these kind of properties here that we often call. So what does it mean to be quasi-random? Well, it's actually not at least not for me, not a well-defined term. It can mean many different things. What it just should mean is that it graphs quasi-random if it looks like in one way or another like a random graph. Yeah. So something is nicely distributed so that I can work with it. And for us, I mean, for us, it's clear what is the property that we want. Namely, we want that every edge, such as this one here, is containing roughly the same number of triangles, because that's the one thing that we used in our calculation, right? How many this fixed triangle, how many triangles can it overlap? And then I said, okay, so I want to know that some edge and how many triangles does it contain. Right. And so we'll prove that if you have this property, every edge is roughly contained in the same number of triangles, then you can actually do this calculation and do your next round, do the next nibble. More precisely, you can prove that if this here is contained, if this condition is satisfied in some round, then in the next round we can cover an epsilon proportion of the remaining edges with the edge disjoint triangles. Yeah, and so that will be my next nibble. And therefore, if in every round I cover an epsilon proportion of the remaining edges with triangles, then of course after R rounds, I'm only left with that many edges. And now if R is large enough, then that of course will get very small. Yeah? And of course what I'm hiding here is that one needs to make precise what this roughly means and so on. Of course there are error terms and they blow up over time and one needs to control this in the right way. But overall, this may be kind of, if you want to make it precise, it's maybe 2 pages or something like this, and not more. Okay, and so now are we quasi-random after one round? Well, because we choose the triangles randomly, and so things get taken out in a very balanced way, and therefore we have a chance to prove we are quasi-random, and then we have a chance again that we can do something random, and so on. So it's really kind of a self-perpetuating process. All right, good. So that's the idea. As I said already, that's just one quasi-randomness condition that's useful in this particular scenario. If you have other scenarios, you might ask for other conditions that you need in order to make your proof go through. And in general, these are very useful. And that's also a big field of things that are studied in combinatorics. If I'm given some kind of quasi-randomness conditions, what can I then say about the structure of the graph or about some properties that it has? Okay, good. So now back to the problem of how do we deal with the leftovers. So if we do our random process, we can cover most of the edges with triangles, but at the end we are going to have a leftover, and we need to decide what do we do with this. And for this, we use something that is called the absorbing method, which again is a very influential tool, and it's not really one tool, it's lots of different ways, or it's more a philosophy, that's what I want to say. And there are lots of different implementations of this philosophy. So what do I mean with this? Let me explain it, and as I said, in a comic version for this example. So the idea is somehow, if we know that we're going to be left with a leftover at the end, we somehow, and we don't have control over this leftover because it comes out of this random process, then we should somehow be prepared for this scenario. So, and we better prepare at the very start, before we even start the random process, because that's when we have most control. Then we still have the complete graph, then we can do really anything that we want. So the idea would be we somehow at the start should find some clever structure that can absorb then any leftover. Yeah. And okay, so the caveat is that it's not really what happens in the end, but let's imagine this is what happens. What do I mean by this? Let me explain this. So let's just assume our leftover just looks like this, and it won't, because it's just very small leftover. It won't be small and so on, and that creates all kinds of problems, and that's why actually implementing all this is very, very hard. But anyway, let's just, for the sake of illustration, we assume that my leftover is like this. But then I'm a bit doomed because I don't have any triangles left, so I cannot cover anything by triangles anymore. But I told you already, well, I want to be prepared for a scenario maybe like this where I'm doomed. And so I can actually do the following. If somehow if I managed at the start to set aside a structure like this, so containing triangles. So I selected these triangles at the very start, which form this funny structure. I mean, it's nice to select triangles because then they form part of my triangle packing that I already found. But now I can use these triangles to absorb these remaining edges. How do I do this? Well, I just switch from the red triangles, which I had included, I switch to the white triangles. And the white triangles have exactly the property that they cover all the red edges, but also the blue edges. Yeah, so I take these triangles out, I don't use them anymore, but I use the red triangles instead, and that will absorb all these edges. So that's the philosophy of the absorbing method. Now, of course, if you then want to go off and actually use this kind of idea in order to really absorb the bigger leftover that you're left with after the random process, you need to do things which are a lot more complicated, and then here the two proofs really differ, and there's even a third proof that is even different, so which is newer, which is very recent. So people have kind of come up with lots of different ways of dealing with these things, but that really kind of about this I could give three more talks. So let me not go into this here. Let me just kind of say that there are some really sophisticated and complicated ideas building on this basic philosophy. Okay.
So when you say a third proof, it's still the same result, the existence of designs?
Yes, but then they want to do more. I mean, now that we know we can get these designs, then we can ask for designs with certain properties like large girth and so on. And so they can use their proof to get. Exactly. All right, good. So that's maybe what I want to say about how we find these designs. I just want to kind of make some advertisement for this combination of random methods, quasi-randomness, together with the absorbing method. This was very fruitful in the area, has led to lots of other really important results, and this is really just a small and a bit arbitrary collection of things that were proved with it, and I don't want to go into it. It's really just more an advertisement. Okay, good. Then what I want to do in the remaining time, actually, when should I stop?
Well, you have a whole hour. I mean, we should leave something for questions at the end, so maybe trying to finish 11:25.
That's fine.
Yeah, okay.
Just so that I know. Okay, good. Right, so let me tell you something about some problems which are related to this, and also show you how they are related, and then I can show a few things that go further. And let's see how much we get. Right, so here are some other objects. So my first object here is a Latin square. I'm sure you all know what it is. I have an n by n square, and I want to fill n symbols into it so that in each row and each column there's exactly, each symbol appears exactly once. Now, for these things, it's not difficult to see that they exist, right? So kind of, I mean, you can do it in this very symmetric way, like here. But there are actually lots of other ways. So here's just some artist that I found online that draws Latin squares. So there are Latin squares which are a lot less symmetric than this one. But so my point is that kind of we've known for a long time that these exist. But now, of course, once one knows that they exist, then one can ask for more structural properties. And that's indeed something that people in the area look at. Can I find what kind of structures do always have to exist in Latin squares or not? Or how many Latin squares do I have? And so Latin squares are also exactly the multiplication tables of quasi-groups. So also from every group you get a Latin square and so on. So there are lots of connections naturally to group theory and algebra more generally there. Okay, what does it have? What does this object have to do with graph decompositions? Well, I can translate it into one as follows. I just draw what is called a complete tripartite graph. So I have 3 parts of vertices, each of size n. One represents the symbols, one the rows, one the columns. And then I draw all the edges between the parts. And then Latin square Bordeaux n corresponds exactly to a decomposition of this guy into triangles. And why is that? Well, if in row 3 in column 5, I have the symbol A, then that gives me one of my triangles. Now, in column 5, the symbol A shouldn't appear another time. So that means we shouldn't use this edge in any of the other triangles given by the other entries. And similarly for the rows and so on. Okay, so we are just answering for kind of finding a Latin square is exactly the same thing as finding a decomposition of this thing into triangles. Okay, so now, since I said that finding Latin squares is easy, then let's look at something a bit more complicated, where things get a bit more interesting. That's what's called orthogonal Latin squares. So, what's an orthogonal Latin square? Well, I have two Latin squares that I put on top of each other. So, and maybe kind of, I think of it as disjoint symbols in the first Latin square and the second Latin square. And anyway, I put them on top of each other. So that, and they have to have the property that every pair of symbols, when I put them on top, appears exactly once. And here's an example just using these playing cards, where I have the four colors and the four, I never know how these things are called in English, but the four is suits, that's suits. Okay. Yeah, anyway. Yeah, then of course I only have one card of each combination, and I want to arrange them in a square so that every color and every symbol appears exactly once in the triangle column. And again, one can ask the question, when is this possible? And this turned out a lot harder, actually. And let me tell you in a second how pattern rewrite comes into the picture here. So that they don't always exist, it's very easy to see. For 2 by 2, then we can't find one, right? So maybe my two symbols are just, if I just have king and queen and my two colors are just heart and spades, then, I mean, if once I put this here, I have to put that there, but also I would have to put it here and there, and then I don't have anything left. Okay, so for 2 by 2, I can't do it. And the question is then, what about other numbers? And here are some other examples for higher numbers, and one thing that you see is missing here is 6, and that's was exactly what is, I mean, by folklore attributed to Catherine the Great. So, I mean, folklore says that okay, she wanted to have from her army, from 6 of the regiments, each should provide 6 officers of different rank, and so that and then she wanted them to march in front of the windows in a 6 by 6 square, so that in each row, in each column, each rank, I never got each rank, and also each regiment should appear exactly once. And then anecdote has it that, I mean, Euler was a mathematician I was at that fort at the time, and so she asked him if he can do it, and he couldn't do it. And then he quickly, or I don't know quickly, but he figured out that one can actually always do it if n is not equal to 2 modulo 4. And right, so he couldn't do it for 6, it doesn't exist for 2, and then he said, okay, then probably it doesn't exist for 2 modulo 4. But unfortunately, I mean, first of all, it took until the advent of computers in the 20th century that we would actually show that for 6 times 6 it doesn't exist, so that's done by computer. But unfortunately for Catherine the Great, it turned out that actually 2 and 6 are the only ones that don't exist. It was then proven in the 1950s that apart from 2 and 6, they always exist. So I mean, she was very unlucky that she chose the number 6. Right, so again, what does it have to, how do I now translate this into a decomposition problem in graphs? That's also easy. I just add another part for the second symbol, and then I get a 4-partite complete graph, and I want to decompose this 4-partite complete graph into copies of K4. It has exactly the same reasoning as before, why we wanted the decomposition into triangles. And so on this level, these problems look rather similar, right? One more part. Okay, good. So that how these problems are related to decompositions. And as I said already, things that people are nowadays interested in, like what kind of extra properties can I ask from Latin squares, or maybe even from orthogonal Latin squares. Okay, let me go to another problem. So all the problems that we looked at so far, the designs and the Latin squares and so on, they all were decomposition problems. I mean, we had a different ambient graph or host graph that we started with that we wanted to decompose. But the objects that we decomposed into, there was triangles, okay, fours or something like this, they were all small. And in particular, if n gets big, then I mean, these objects are small compared to n. So now I want to quickly look at the problem where this is different now, where I decompose into something which is large. And that is a story that starts actually close to here. So there was this funny little periodical, the Ladies and Gentlemen's Diary. Yeah, let me read because it's so this is designed particularly for the amusement and instruction of students in mathematics, comprising many useful and entertaining particulars, interesting to all persons engaged in that delightful pursuit. And then, but so somehow people could write to this periodical. It was printed in London here. I think, not Gates. Anyway, people could write and ask some questions there. And I mean, for many of them, I'm actually not so sure what it has to do with mathematics. Somebody asked about what was the original of the national anthem, God Save the Queen? And is it in any way connected to the diary? But anyway, so, but somebody named Kirkman, who worked for the church, he posed a problem which kind of even I would consider more mathematically. He posed the following problem. So, and you should think, I don't know, very strict English boarding school here or something like this, with a strict matron. So she has these 15 young ladies that she thinks they have to go for a walk each day. And then they should walk orderly in rows of threes, but in such a way that not two of them walk in the same row for more than one day of the week, because otherwise they start to talk too much or something. And okay, so anyway, he asked, is this possible? And then he actually, for the next version of the periodical, he answered his question himself and gave a solution, but also some other people wrote and gave a solution. So this is possible, it turns out. What does it have to do with decompositions? Well, again, I can draw a graph, and now it will be, again, the complete graph on 15 vertices, which are 15 ladies. And on each day, I want to group them in groups of 3. That means on each day, I want what is called the triangle factor in this complete graph, meaning triangles which are now vertex disjoint. Yeah? So the triangles cover all the vertices, but they are vertex disjoint. And this represents one of the days where they walk in these groups of 3s. Okay, so that's one day. And then the second day, I get again a triangle factor. Maybe this one, where I group them differently, again, vertex disjoint red triangles here, but I'm not allowed to reuse any edge that I've used already. Yeah, so I want to pack these two things. And then I continue with the next day, and so on, until and then you can do the math to see that actually you have to, if you do the 7 days, and that's why the numbers are like it, if you do the 7 days, then you use each, and you can do it, then you use each pair exactly once. Yeah. So this is this asks for a decomposition of the complete graph on 15 vertices into these triangle factors. So not single triangles anymore, but really triangle factors, where each factor consists of these vertex disjoint triangles. So this is a large object covering all the vertices, and that makes this decomposition problem a little bit different. And there are other problems which similarly are different. Okay. Now this again we can translate into a but funnily enough, this problem, even though it's different, we can again translate it into a decomposition problem for small graphs. And that's why we also know how to deal with problems of this type by now. So how do I translate it into a problem of small graphs? I'm drawing this graph now. So I have my original complete graph with 15 vertices. I add another part where I just make all the edges between there and here. And now I want to decompose this thing into K4s, into complete graphs of size 4. And if you think about it a little bit, it's clear that in such a decomposition, all the copies that you can select are this, because you somehow have to cover all these edges. They have to be of this type, a triangle over here and a vertex over there. And if this is the case, then we can look, and I didn't draw the edges because that gets messy. But what this picture means is these are now, each of these triangles forms a K4 with this vertex up there. These are exactly the K4s that I use at this vertex. And then, of course, these triangles have to be vertexes joined because otherwise I would reuse one of these edges. And that's true for all the vertices. So I have translated this problem into that problem. And we can deal with problems like this because Böttcher actually did a generalization of his result for more complicated settings than this setting of the designs in the complete graph. For settings where I'm allowed to have such hard-tight structures, and then I'm also allowed to have other things on top, but this I don't need here now. So just to mention it. All right.
Sorry, I have a question. So is it the case of something that was not known before for graphs, and out of Kivaish's results for hypergraph, could we specialize to the case of graphs and get these special kinds of decomposition?
I believe that is true. Triangles was known, I think. I'm not even sure about that's. I think it wasn't known for graphs actually. But okay, I don't want to be sued about this. So. Right. Good. And so let me just mention two more problems, and then I stop, and I will mention them very quickly. Here is one generalization where I ask. Uwe Böttcher is a mathematical science institute, and if you've ever been to a meeting there, you will know that you will get randomly put to a place at dinner. So you have tables of different sizes where you sit, and you will get put randomly to a table each meal. And that's why a combinatorialist, Ringel, asked at one of these meetings, well, can I actually make a perfect seating plan for such a meeting? So, of course, only if the numbers match up. What would a perfect meeting plan be? Well, of course, a perfect seating plan would be that every participant sits next to each other participant exactly once during the whole meeting. And this corresponds, again, to a decomposition of our complete graph, but this time not triangle factors, but what we call cycle factors. So each cycle represents one of the tables, and these cycles and these tables now could be big, depending on what tables we have. And that makes this problem, again, a little bit different than the problem we saw previously and also harder. But so we have all these tables, and each table is represented by a cycle because if people sit around the table, of course, only these people sit next to each other, and this one doesn't sit next to each other. And now we want a decomposition of the complete graph into these kind of objects. And that's also something, that has been done. I'm sorry, I didn't write it down and I didn't get names. But this is something that has, again, been done by different groups of mathematicians to show when is this possible for large n again. And it starts off from similar techniques as I've shown you, but then you need to add a lot of things on top, so it gets more complicated. Okay, now problem I want to finish with, because that's I have done some work, so just to mention in half a minute maybe, is the following conjecture, which is very nice. I like it very much. It was, I think, still as a master student, somebody mentioned it to me, and already then I liked it very much. And it's the following: we have some trees. I mean, you are allowed to give me some trees. Tree number I. The only thing I'm asking you is that tree number I has exactly I vertices. And then you give me trees from T2 up to Tn. And it's my number of vertices. And then the conjecture claims that no matter which trees you give me, we can pack them in the complete graph on n vertices. And this actually has to be a decomposition. Why is this? Well, tree on I vertices is exactly I minus 1 edges. If I sum up these I minus 1 edges, then I get exactly n choose 2. And that's somehow what makes the conjecture a bit magical. Because also, I mean, at least I tried to talk to a lot of people, of the older people in the area. where people had the intuition for this conjecture, and they said, well, probably there wasn't much, because for a long time one couldn't prove much. There wasn't much, apart from that the numbers are somehow so magical, right? So this is still open. We still don't know that this is true, and it's not even for large n, we don't know, but we know quite a lot. So here is this is really just a combination of a lot of work I've done in this area, but also many other people. So we also rely on the work of lots of other people. So sorry for not being complete with the attributions here and so on. But by now we know that this is true as long as the trees don't have too large maximum degrees. So maximum degree of the trees should be at most Cn divided by log n. Yeah. So then we can do this. Still open whether it holds in general, and I don't know. I change my opinion every few months, so whether it's true or whether it's not true. But that's certainly a problem I'm still very much interested in. And the proofs in this area, they're built on the things that I have shown. We also use random processes of different type, but we also use the Kivash result, and there's a lot of additional work that you need to put in to get there. Okay, so that's maybe. So I wanted to show you a little bit what kind of things do people work on in the area. These are the kind of things, and there's actually quite a number of other things. Okay, so let me start with this. Stop with this, and just leave you with this little poem concerning the unscrewable problem. Thank you.
Maybe I'll have first question. Can you just quickly say, you said you use Kivash's result, the result itself, or use the methods, or maybe both?
So the question was if we use Kivash's result or the methods of both. We use his result, and we use the more general result that works somehow in an apartheid setting and allows some colors and so on. So this is a horrible picture, and I won't explain it. But anyway, so we want to decompose in some setting where we have apartheid and have colors and also have some directions of some edges. We want to compose into objects like this one which is not dotted. So anyway, and he has a result that readily does this for us. And for us, this result, of course, so at the beginning I said for the designs, we need to have certain conditions satisfied so that we find the designs. Now, one is actually in a different setting here where one doesn't work, of course, in the complete graph anymore, but one works in a quasi-random graph. And so and also we are in this more complicated setting, and then the conditions that one needs to satisfy, they get more complicated. And most of the work, and it's kind of almost 100 pages, unfortunately, is getting yourself into a position so that you have these conditions satisfied so that you can apply the result. Yeah.
Thank you. Do you have any questions in the room? Do you have any questions? No. Okay. No questions in the room? Yeah, sorry, go on.
I have a question about the Laplace square problem. It seems to be that the quasi-random method works for larger terms. The only impossible cases are 2 and 6. What is the method used to handle small net?
No, these
Just repeat that.
yes, sure, that's right. So this was about orthogonal Latin squares. I mean, I said it was proved that they always exist apart from 2 and 6. This was actually done by completely different methods. That was, and I actually don't know, I must admit. So that was, done before all this machinery came. So it's somehow easier, this problem, I suppose.
May I ask another question?
Of course.
Yes. So in the original P3 decomposition problem, I don't see where the divisibility condition is used in the quasi-random.
Okay. The question was in the original triangle decomposition problem, then where is the divisibility condition used in the proof? Well, of course, when you do the random methods, you don't need it for this because you don't want an actual decomposition. So that has to be used then at the end when you want to do the absorption. Yeah, and it's clear that you need this condition, right? So it comes in this part. Because otherwise you don't get the right number of edges.
Yes. Yes, thank you.
More questions? No? let's thank you again.